Okay, so we've created this function, very simple function, and now we can use it on the command line. So, for example, if I want to set up a new variable called s and make that equal to function, easier to copy it, but anyway, I'm typing it out again. This should return a value equal to 1. Let me correct the spelling mistake. Hit return on that. That gives me 1, as I'd expect. We set x equal to 0. We return the value of the function is equal to 1. But I could also do this for, rather than a scalar input argument, a vector input argument. So if I wrote down, let's set up a vector v equal to this, for example. Now I use this as the input argument. I can call the function again. Use the up arrow, and then I can edit this. So I can call this now t, let's say, and I change the input argument to v. Hit return. Then gives me, for a vector input argument, it gives me a vector output argument, where each element is corresponds to the input argument. So this is the original. This is the same as we got before, x equals 0. This is the value when x equals 1, and this is the value when x equals 2. Okay, so we've set up the function. So if we now go back to the worksheet, we've created a MATLAB function to calculate that. We can read the book. Second task, we can read a section on the ebook, Essential MATLAB for Engineers and Scientists, to implement the trapezium rule as a function. But actually, the trapezium rule is also covered in your textbook, the Croft Mathematics for Engineers textbook. On page 826, the block 4, computational approaches to integration, that explains how the trapezium rule works. And it's probably something that you've already seen if you've done A-level maths at school. So we're calculating the area under this curve between x equals a and x equals b. And we do that numerically by dividing the area under the curve up into trapezia, each of width h. And then we can calculate the area of each trapezium, which is just this. Well, this is the area of the first trapezium. The area of a general trapezium is just this. And then we can add up all the trapezia between our lower limit of integration x equals a and our upper limit of integration x equals b to come up with an approximation for the area under the curve. So it's a numerical approximation of the area under the curve, or numerical integration.